So hello everybody and welcome to our presentation called Burning Asgard. It's an introduction into the tool we call Loki. Within the research team which produced the work we are showing you today was a guy called Enno, my colleague Daniel Mende, and myself. I'm called Rene Graf. Some of you may notice that my name was not on the agenda, but it was Daniel and Enno. Unfortunately, Enno cannot be here today due to some family reasons. So Daniel and I will doing the talk today. So yeah, thanks for showing up, and I hope you enjoy the next good hour. So, who are we? We are some network geeks, security researchers working for a company called ERNW. It's based in Germany. The company is mainly doing penetration testing, security researching, security analyzing, developing concepts, stuff like that. And doing our research work, we are fiddling around with network devices, trying to do some nasty stuff with them, with the devices and with the protocols, and that's pretty much making the majority of our days and work. So the company, one more slide. So the company is based in Germany, in Heidelberg. So some of you may know that. I won't tell you too much about that. One point which is our main understanding is that we understand corporate. If we do mitigating controls or telling companies what to do, we always think about their business, that it should work. So we also have a blog, maybe also some of you know this already. It's called insinuated.net, and we also have not comparable to Blackhat, but a really small conference, which is also hosted in Germany. Some of you I also saw there. So the agenda for today is why Loki? What is Loki? What can you do with Loki? And why does the world need another tool doing nasty things in the network? Next point would be the tool itself. For that, Daniel will tell you some architecture stuff and how it was coded, because he was the main coder of the tool. So he can tell you the internal stuff best. And the last point of the agenda is some advanced attacks which were also implemented inside this tool, but you will see it. Good, what do you see here? I hope most guys of you should recognize this screenshot. It's pretty much only a Wireshark. And a lot of times when we are in company networks, our customers, our client networks, and we fire up a sniffer just at the client network port, we see stuff like that. So it's nothing special, but what special do we see here are the infrastructure protocols. They talk, you pretty much see this in lots of networks, routers talking infrastructure protocols in the wrong networks. So mostly there's no reason, for example, to talk OSPF in a client network, but you still see this stuff. So this results very often in some scenario which can look like that. If we give a report about a security assessment, or we tell our customers, okay, here, you have some problems with your infrastructure protocols. They can easily be attacked. There are security concerns about that, and this can cause serious harm to your network. This ends up the customers telling us, okay, it's just theoretically. Show me the attack. Show me how you reroute our traffic in the network. And then that's where the problem comes up, because there are not that much tools you can use to show them this stuff. So most likely these security incidents we mentioned to the customers, they won't going to be cured in any way. They just ignore it because it's just theoretical stuff. Yeah? So that was the idea behind the tool. So we thought about, okay, some of the attacks are nothing new. They are widely known that some of the infrastructure protocols can be attacked very easily. But what we will try to do is to close the gap between the theoretical attacks and provide a practical tool for that, so you can perform these attacks in an easy way. So you can show this to your customers. So, okay, here's the problem. I do 1, 2, 3 mouse clicks or enter some commands, and then I can redirect traffic or hijack some routers, whatever. So that's the reason why we provide a new tool for that attack, to close the gap between theoretical attacks, mainly based on infrastructure attacks, and practical stuff, make them work. Yeah. So, and we suspect that if these attacks were not just theoretical, if you can show them to them, so in 1 or 2 minutes you can perform an attack, you just explained them, okay, that's your problem, then that would most likely change the stuff. Yeah. There are some tools that did the same in the past. One very popular tool, I'm sure some of you will know this tool. It's called Cain and Abel, and it pretty much changed the way people look at some special attacks, because since the release of that kind of tools, the attacks can easily be performed by everybody. You don't even have to know how an attack works in the background, because you just have to enter some information, press a button, and then the attack goes. But you don't have even to understand what is going on in the background. So we believe that this would change a lot of things, how people, customers, or other people are looking on vulnerabilities, if they are practically doable, if they work, or if it's just theoretical stuff. Somebody's telling you, okay, there's a problem, but there's no tool, there's no way, no easy way to exploit these vulnerabilities. So there's where our tool comes into place. We call the tool Loki, and I will tell you something about this tool now. So just to complete this, here's a small overview of tools already exist in the wild that can do similar things, but most of them are really complicated to use. There's a tool called EarPass, it's pretty old already, which can handle some routing protocols also, but mostly only in discovery mode, so it shows you some information about the routing protocol implemented in that network, but you can't actively exploit something. Another really great tool is Yersinia. It's mainly layer 2 attack suite. I'm sure at least some of you also know these tools. That's also one of the tools that pretty much changed lots of things, so closed the gap between theoretical attacks and practical attacks, because it made it usable for everyone without knowing deep details or writing complicated scripts or whatever. Some other tools are like HPing, Nemesis, Scapy. I don't know if you know these tools, but maybe one of you has ever used Scapy. It's a pretty much powerful tool. You can use a lot of routing protocols also with that, but it doesn't implement any state machine. So you still have to write complicated scripts which handle specialized attacks, and you have to invest much time to make some attack work. You can do it with that, but it's pretty complicated. You have to write scripts and all that stuff. So it's not easy to use. Good. Back to our tool. What does Loki provide? Loki provides an GUI, so you can easily use it. You don't have to use a command line interface at all. The initial idea behind Loki was to combine some of our own written command line tools, which were already released in the past. For example, about 1 or 2 years ago, Daniel and Enno had a talk about MPLS and BGP security, and also released some useful command line tools. But still, we noticed they're not used pretty much because it's maybe too complicated to use them. It's not easy. Just run an installer, click some buttons, and perform attacks. So the initial idea was to just combine these tools in an let's call it infrastructure protocol attack suite. To combine these, have an easy GUI to use, and make these tools more usable so the people will also use it. Because if you write a tool, normally you also want the people to use that tool. Why else would you have spent lots of time coding some tools? In the meantime, it's not just a collection of other tools implemented again in a suite. It's a lot of more in the meantime. It has a module architecture. Daniel will tell you something about the module architecture later. So you can easily implement new attacks, add new routing protocols, are able to use some low-key modules within other modules. For example, use an MD5 cracker module to crack an OSPF routing protocol authentication password or something like that. So you can combine different modules, all that stuff. We have also lots of protocols implemented already. They are already working really fine. You will see that some slides later, which protocols they are. Nearly every protocol is an infrastructure protocol. Some of them are, well, let's say lame. There are lots of tools existing already, but we still had to implement that modules because the other modules depend on that. So you don't have to fire up a command line and do ARP spoofing in the background before you can actually perform another attack. So we wanted low-key to be able to perform the whole attack on itself. Don't need any other tools anymore, at least for that kind of attack. Low-key also includes a new version of a tool called MPLS tool. It was also released at the Blackhat talk in the past covering MPLS security. And there's a new version included with it. That's the only part not implemented as a module within our tool. This is a special reason. Daniel will tell you about that later. But if you install Loki, you also have this requirement installed also. So that's the point where Daniel comes on.
Okay. So first of all, hello. So I will give a short overview and introduction into the main program. So first we will have a look at the architecture, then I will tell something about all the modules that are there, and afterwards we will have a look on the GUI and how it's built up. Okay, so first the architecture. Loki is mainly the main program, which is called Loki. It got a very open module API, so every module just don't need to deal with any networking stuff, don't need to deal with a lot of graphical stuff. This is all handled by the main program. You just focus on your protocol you want to implement. So first I had made some library extensions to, for example, get IP tables firewalling working with the libdnet, but get away from this again because I noticed, okay, it's not possible to roll out patches to some system libraries. So in the meantime, you don't need any library extensions anymore. You just need the library dependencies and the main program. Okay, so there are a lot of protocols already implemented. You see the whole bunch of lists. Let's begin with ARP. Okay, ARP isn't anything new. There are a bunch of tools doing ARP spoofing, but as Rene mentioned, I'm implemented it as well, just to give a suite which with you can perform the whole attack from the start to the beginning. And if you need to be in some kind of man-in-the-middle position to perform some attack on a routing protocol, you can use Loki as well. So there are two modules, the EIGRP and the WLCCP one, which are not released yet because there are some legal issues with Cisco on that protocols, because EIGRP and WLCCP are both Cisco proprietary. On WLCCP there is also a patent application from Cisco, so we don't get into any legal trouble. This is why we won't release that modules now. Okay, I'll give you a short overview of all the attacks which Loki is able to do. So first there is the ARP module. As you can think of, it can do ARP spoofing, it can do ARP scanning, and implemented also an ARP flooding mechanism. So there is a module for BFD, which is a brand new protocol. The RFC just showed up beginning of June. Which is some kind of protocol for doing hot standby and failover mechanism. Rene will tell you something more about that protocol later on. Okay, I also implemented the BGP part of my old tool, the BGP CLI. I gave it a graphical user interface, so you can do NLRI injection with that tool. You can inject routing information into some BGP domain. There is also a module for EAGRP, which, as I said, will not be released now. Maybe in the future, not quite sure yet. But with that module, you can also inject EAGRP type length values, which are in fact routing information. And I also implemented 2 older attacks against EAGRP, which are the authenticated and unauthenticated denial of service attacks. And then there are 2 modules for HSRP and HSRP version 2, which is just a hot standby protocol for IP addresses, and with the Loki tool suite you're able to take over one of these IP addresses. So there is another module for the LDP, the so-called label distribution protocol, which is used within big MPLS backbone networks. You can hook into the LDP process and can inject label mapping messages. You're also able to attack some layer 2 over MPLS tunnels and establish your own tunnel and all that fancy stuff that LDP is able to. If you want to go deeper into all the LDP and MPLS stuff, I recommend you to take a look at our last year Blackhat talk about exactly that topic. That topic, which covers LDP, BGP, and MPLS. So there is an MPLS module as well, which can rewrite the MPLS labels, which also can discover different MPLS traffic paths. And there is also, like Rene said, the MPLS TON program, which gives you or your machine some kind of MPLS VPN-enabled network stack. So you just pop up a virtual tunnel interface, when all traffic that you put into that tunnel interface will be MPLS labeled and thrown out to the network. Okay, there is an OSPF module. With this OSPF module, you can hook up into an OSPF routing process. You can inject OSPF routing information and also implemented an OSPF MD5 authentication cracker. So even if you're, well, okay, you will see later on. We will have a nice demo on this one. I wrote a RIP module. This was more like some kind of typing lesson. It wasn't that hard. RIP is a really easy protocol. You can do route injection with that as well. You don't have to do any handshake, so just throw the routes on the cable and they will get into the routing table. Okay, there is a TCP MD5 module with which you can crack the RFC 2385 TCP authentication option, so which is mainly used by BGP and LDP for authentication for authenticating the neighbors. So if you see one of these packages, you can also do a word list of brute force cracking on the password. There are 3 more modules, which is the VRRP and VRRP v3, which are also for IP address, hot standby, and fast handover. So you can just take over one of these hot standby IP addresses as well. And there is the WLCCP module, which was the main part of our last Blackhat talk in Europe this year, which is the wireless LAN context control protocol, which is also a Cisco proprietary protocol for building up a wired distribution system. And we take some work into analysis this protocol and do some crypto analysis on the authentication mechanism, and it came out that it's all based on LEAP authentication, and as you all should know, LEAP isn't really secure. So in the end, if you use this module, you will get the pairwise master key of wireless clients. Okay, Loki also has a graphical user interface. It's based up on GTK. I'm using PyGTK because it's really easy to program in Python, and I don't like GTK on the C interface. It's a pain in the ass. The main program has some hard-coded GTK window routines, which are the main window, there is a configuration window, there's a log window and stuff like that. But the modules themselves, I decided to use Glade for the task, because with Glade you can easily design your interface and click a button here, click some input line there, and afterwards you will get a nice XML file, and that will be passed on runtime. But that means also that you can change your module GUI on the runtime. Or, let's say on the runtime of the main program, you always have to reload the whole module to get the new graphical user interface. But it's really easy to involve all your modules, as they can be reloaded on runtime. And so it's really easy to fix some bugs or do some testing and put in some new code. Okay, this is a nice screenshot of Loki, but you will see it in action in a second. Okay, I will hand over to Rene again.
This one.
This one. Oh, yeah.
Thanks. So as Daniel, as you can see, there are lots of attacks implemented already in different modules. Some of them we will cover today. For some of them we will have nice demos, should be 4 in total. Others we won't cover because they were already covered in other talks, and which are just integrated to have a more usable tool. So we told you lots of, we have that module, we have that module, we have that module, but okay, what can we do? What kind of attacks can we do with our tool? So what's the reason? Why should one attack a routing protocol? What benefit does someone get out of the attacking a routing protocol? So to give you an idea about that, we will now have a short discussion of some of the attacks implemented in Loki. It's just not possible to cover all in this kind of time slot. So I don't know how deep you are into network protocols, routing protocols, whatever. So I will give you a short overview about that. Routing protocols in general are used between network routers to exchange information about their connected networks, about how they can reach other networks, how far the networks are away, for example, if it's a good option for another router to use this router to reach a network. So routing protocols do this dynamically, so they can act upon link failure. If an interface goes down or a line is broken, it can just switch over to another one, so the network's still reachable. There are 2 kinds of routing you can use. In small networks you can use static routes, but in large networks with several hundred, several thousands of nodes, of routers, of networks, you can't use static routes. That would be a really pain. So you need some protocol handling your routing information, your network information to get the stuff working. Unfortunately, the internet would not be working without routing protocols. So there are different flavors of routing protocols. First are the interior gateway routing protocols, or the interior gateway protocols, short as IGP. They're mainly used inside our so-called autonomous systems. So you will find protocols like this inside a corporate network, for example. Any scale of network can use these networks. One of the most famous of these kinds of protocols is the OSPF module. If you go to, let's say, 10 different big networks, you will find it at least 5, 6, 7 times using OSPF as a routing protocol. So inside corporate networks, inside closed networks, you don't communicate with interior gateway protocols, with other networks, with other domains, with the internet or whatever. The other kind of routing protocol are the exterior gateway protocols. There's mainly one exterior gateway protocol. It's called BGP. The internet uses it to exchange information about the connected networks, how they can be reached, where they are located, alternatives routes to that networks if one link fails. So that's the one you will find in the internet. Yeah? The internet routing stuff is handled by BGP. In some really large corporate networks, you can also find BGP. Some guys implement this also, or use it as kind of an interior gateway protocol and use BGP inside the corporate network. So for the routing protocols, there are different ways to do their work in general. So totally different categories, concepts behind these routing protocols. One of the oldest one is the distance vector routing protocol, or distance vector protocols category. Protocols like RIP, which is not used anymore, or really rarely used. And it's enhanced IGRP protocol. The distance vector protocols mainly exchange information with their neighbor routers about how they reach which network. So router A maybe tells router B, I can reach the network 192.168.0 via 3 hops. 3 additional routers, it's 3 hops away from me. So if you don't have a better path to that network, just use me as your router. I will manage to get this network there, to get your packets there. So this is pretty much distance vector. Which network can be reached with what distance? How far is it away? So, the other ones, the link state protocols, these are, let's say, the newer ones, like OSPF or ISIS. They don't exchange information about all their networks they know. They just exchange information about their directly connected networks, which are not reached using another router. So they tell their neighbor, I have 1, 2, 3 links. There are these 3 networks, and these are my neighbors. So after the initialization of a link state protocol, it's a little bit simplified, but let's explain it on a small network. Every participating router knows the complete network layout. So they don't rely on distance information, but they know by their own, if this link is broken, I can reach that network over the other way also. So it's a complete different kind of routing protocol. They exchange link state information, who are my neighbors, what networks I am directly connected to, and distance vector protocols exchange information of which network do I know and how do I reach it, how far is it away. So different kind of information that is exchanged. A third kind is a path vector protocol that's used by BGP. I don't cover this here in detail because the talk doesn't cover BGP today, so it's not necessary. But it's a little bit similar to the distance vector protocol, just I don't exchange information about networks, but information about autonomous systems, which are many networks. Good. So that are the kind of routing protocols and the purpose of routing protocols in general. So why should we attack routing protocols? So what has already been done on the topic attacking or security of routing protocols? There have been a talk at the DEF CON in 2008 by Capella and Pilosov. There was a talk at the Blackhat 2009, that's the talk we just mentioned, it was about MPLS and BGP. There were some, let's say, incidents when something bad happens to a routing protocol. Let's say the YouTube Pakistan incident. Some of you may remember that. Pakistan tried to block YouTube by advertising the YouTube network inside the Iran. And that did some error, and it was advertised on the whole internet, and nobody could reach YouTube anymore. And there are also some other incidents when something get wrong with a routing protocol. Most likely there are human errors, what happened there. Also, there's not too much discussion about routing protocol security in general. There's an RFC, it's called Generic Threats of Routing Protocols, which covers, okay, what bad can happen, the bad things that can happen to routing protocols. There's an IETF draft on OSPF security vulnerability analysis. There was a presentation about, with a proof of concept on attacking OSPF networks, also injecting routes, but it was, let's say, a small proof of concept program, which was hard to use in real attacks because it just worked in some special scenarios. And there's also an IETF working group. There was an IETF working group handling routing protocol security, but they concluded their work, I think it was last year, beginning of the last year. So that's pretty much the things that already happened against routing protocols. Let's look at the definition, or at one part of this RFC covering generic threats routing protocols. I could now just read it down, but everybody can maybe read it themselves. It ends up in two attacks. It's one kind of attack is the traffic redirection, but in a larger scale, a typical let's say, for example, an ARP spoofing attack redirects traffic between two hosts, or maybe between a subnet and a host. If you attack routing protocols, you can redirect whole networks, and not only traffic for single hosts. And when you do nasty things with routing protocols, of course, you can perform denial of service attacks. So if you manipulate the routing information so it can't work anymore, so that's a kind of denial of service in general. So what you can do with routing protocols is inject incorrect routes, so which will happen in the traffic being directed to the wrong routers, not to the routers they should go to. So maybe it could be your laptop and you forward it to the real router, so you can eavesdrop the traffic, do man-in-the-middle attack actively, all that stuff that needs traffic redirection as a basis. Yeah. So that are mainly the bad things that can happen. Traffic redirection with eavesdropping or man-in-the-middle attacks, and denial of service attacks. So then let's go to the first protocol and the first demonstration we have. OSPF stands for Open Shortest Path First. As I already told, it's one of the most widely used routing protocols inside corporate networks. It also belongs to the category of the link state protocols. I already told you this also. If the routing injection, so what we will try to do is inject or redirect a route, which should, the packets for a network should end up at a special router. We redirected our laptop, so we are able to eavesdrop the traffic or do man-in-the-middle attacks, stuff like that. If this will work actually in an OSPF network, I won't dig too deep into the OSPF theory now, but if you have an OSPF managed network, the different networks known inside the OSPF network can have different types. So, and there are some types of networks, for example, the so-called totally stubby network, which is a network which only can have one router. So all systems on this network only have a default route. It's not possible to inject other routes. The OSPF router won't accept this in general, but that's by design, so you can't perform attacks within such a network. But nearly every other type of network will work. There are also some protection mechanisms which should prevent false routes from being injected. One is the so-called OSPF fight back mechanism, which mainly is a feature if, let's say, I have an OSPF-enabled router called router A, and it receives some routing information telling the router, hey, I can reach this or that network, but this router is responsible himself for that network, so he knows, hey, there's something wrong. So he will re-inject the route himself and prevent the redirection. But that, in most cases, that does not really protect against false route injection. So it's mainly against misconfigured routers that are added to the network. So that's the point where the first demo will take place. We have a network setup. It's pretty simple. It's two routers connected with one network in the middle of them. Let's say it's a backbone network, and we have an attacker, this laptop, sitting in the middle and fiddling around with the routing protocol to redirect the traffic. But then you will tell you the details about the demonstration.
Okay, what you see here now is the command line of one of the two routers you see in the front here. And what I will do first is show you the routing table, which looks like that. Okay, we got some routes into the 192.168 net. We got some 172.16 routes. But don't mention all the different routes. The important thing is that you don't see any, let's say, 10.0 network. So if there were a default route, all traffic going to the 10.0 network will follow that default route. Okay, so there is no route into 10net. I think we should change this because I want to be the 10.0 network myself. So what I will do is just launch up Loki, which is this nice tool. So, and now I will just select an interface. I will listen to, I've prepared different demos on the same setup, so you will see some VLAN configs here, and I got different IP addresses. So, but for that demo, I need my real ETH0 interface, and when I click on OK, the tool will just start listening for packages on that interface. So, and you see there are some of these tabs blinking, so it also discovers some routing protocols, which in this case is OSPF, because this is the OSPF demo, yeah, obvious. Okay, so we got two hosts speaking OSPF in that network. So, okay, let's just hook up to them. I will just change the authentication to none as they are using non-authentication, and afterwards I'll start participating into the OSPF process. So I'm just starting to send out hello packages, and when one of these routers see my hello packages coming in, they will perform the OSPF handshake with my tool. And once I'm in the state full, I got all the routing information from that routers delivered via OSPF. So you see that are all the routes those two routers exchange between each other. There are some different kind of routes, as Rene mentioned. There are some stub networks, there are transit networks, there are point-to-point links, but there is no totally stub network. So it looks like we're in quite a good position to perform an injection attack. So what I do next is just go to the injection tab and type in, okay, I said I want to show up a 10 network. Let's say it's a square 16, and okay, it's a route link, so it's directly connected to my router. I'm not really a router, but I'm telling all the OSPF router, okay, I got a link into the network. So once I add this route, the link state update gets thrown out to the OSPF routers, and yeah, in a second or two you will see right there is my route showing up. So the router is just repeating that information to me, saying, okay, I understand you, I know there is a route into the 10/16 network. And when we look back into the router's command line, you will mention there is, okay, some new OSPF neighbor showing up, which means I successfully performed the whole OSPF handshake. I'm now part of the OSPF network. And if we take a look at the routing table afterwards, you will see there is a new route showing up for the 10/16 network, which points to my local notebook. So every packet which should be routed into the 10/16 network is now redirected to my notebook. And I can do with that traffic whatever I want. I can sniff it, I can perform man-in-the-middle attacks, I can just redirect it to some other router to keep the traffic in flow, to get the traffic to its final destination. But the important point is I will get all that traffic. Okay, so that's the first part. Rene will now continue with the next protocol.
So as you saw, Daniel just injected a new route into the routing tables of the participating routers, which if you do it in both directions, advertises a new route to that router, and a network originally based behind that router to the other direction. So every traffic between these two networks will be redirected over the attacking system. In this case, it's a notebook, so you can do with the traffic whatever you want. So the next thing is, same thing with the enhanced IGRP protocol. I already told you it's a distance vector protocol, but it's still used in some locations. I call the locations, let's say, Cisco shops, so companies really sticking to Cisco, buying the switches there, the routers there, every equipment there, so there's a good chance they're using enhanced IGRP as a routing protocol. You can do that only if there's no need for interoperating with other manufacturers. So because other manufacturers won't speak enhanced IGRP with you. If you have a mixed environment, you can't use that protocol. But in plain Cisco environments, you will still find the enhanced IGRP protocol. Yeah. There were also some security discussions back in 2005 about security in enhanced IGRP managed networks, but since then, at least I don't notice anything more happening on that topic. There was no tool being able to perform these attacks, which were discussed there. That's also another reason why we implemented that or mainly Daniel implemented the stuff in Loki. And now you will see a similar demonstration to the OSPF demonstration, but just using another routing protocol. So,
okay.
Down to the next demo.
Let's switch over to my notebook again. So that's still the same router's command line interface. When we take a look at the routing table again, you will see there is no route to the 10/16 network anymore because I disconnected my tool and the OSPF state just shut down, so also the route got deleted.
Yeah, and this letter indicates where the route's coming from. It's connected, it's OSPF, and later we'll see the enhanced IGRP.
Okay, so let's launch up Loki again. And this time I will start sniffing on a different interface, which is just another VLAN on the setup. And in this VLAN there is no OSPF spoken, but you see it just discovered some routing protocol, which is the enhanced IGRP. Okay, we see there are two hosts speaking enhanced IGRP. They're both in the autonomous system 1, so they're part of one routing infrastructure. The first thing I have to do is participate in this enhanced IGRP autonomous system. So I have to send out hello packages again, and both router will perform some kind of handshake with my program. You see in the background, okay, there is a new enhanced IGRP neighbor showing up, which is my notebook, and you also see there are routing information delivered by the two routers. So now I have to choose, either I want to inject an internal route or I want to inject an external route. I will just do the same as the demo before. So I will configure an internal route which just points to my notebook, which is this IP address. I also decide to take /16 network, and my destination again is the 10.0 network. So I will inject this route into both routers, so I have just to mark them and afterwards sending out those updates. So you see one of the routers instantly repeat that routing information to my system. And if we have a look on the routing table, oh, that's the wrong one, sorry. So if we take a look on the routing table, you see there is a new route showing up to the 10.0/16 network. So we also successfully injected some fails routing information into that routing process. So again, all traffic to the 10/16 network will be redirected or routed to my host. And I can do whatever I want with that traffic. Okay. So back to Rene and the next demo description.
Okay, so we are just walking through demonstrations now. There are some routing protocols, like OSPF has a feature like that. That's because I'm going to tell you about that feature here. Some routing protocols have some authentication features. So There, like for OSPF, there's some shared key, a password you have to know to be able to inject routes, because the routing information will be authenticated. Not a lot of networks are really using that, and if they are using that, there are most likely stuff like HighSecure, Cisco, whatever, because and also they never change, because if you have, let's say, 200 routers communicating within each other, it would be difficult to change the key everywhere. So if they use routing authentication, it's most likely to be a weak password. I'm pretty much amazed what kind of words people invent for password. Sometimes it's key, then it's community string, pre-shared key, password, whatever. All have the same problems. If they're weak, they are easily breakable. Not that's a really new thing to be able to break, let's say, an MD5 hash or something like that. But as I told you at the beginning, we want the stuff to work. We want to be able to combine different modules, so we can just enable the authentication feature in low-key, and we'll take the packages, try to crack the password based on a word list, and again be able to inject routes. And it's pretty much similar for the different routing protocols. I'd say OSPF is widely deployed. Some also use the authentication. So the next thing we will show you is a demonstration of how we can inject or how we can crack the password or the OSPF authentication key. And after it's cracked, it's the same procedure as in the first OSPF demo to inject the routes. If you have the password, it's no problem anymore. So, Daniel, next part.
So it's the same router again. We will have a look at the configuration first. So I will show you the configuration of the interface I'm going to attach in a second, which is the fast Ethernet 0 on the VLAN 20. And you see I've configured an OSPF message digit authentication on this interface. So every OSPF packet sent out on this interface is authenticated using the secret string secret. So when I try to hook up with low-key to that OSPF routing domain without authentication, my packages will just get dropped. So, okay, I will hook up into that net again. So I will launch low-key and select the third prepared network. After I start listening, or after some seconds, there will show up some new routing protocol, which is the OSPF. And this time, you see both hosts use the cryptographic authentication. So I need a password to perform the OSPF handshake with these two hosts. So what I will try now is just to select some word list. I use this one. You can easily guess the password is in there because it's just a demonstration. If I use the brute force here, you will sit here until next week. So I will keep the demo short, and I put the right password into the work file. So, but just to show you how it works, I will select one of these hosts, and with my Word file, I just try to, let's say, brute force the MD5 secret. And after a few seconds, there are about 4,000 passwords in that Word file. So after a few seconds, or not even a few seconds, the tool finds the right secret. So you see, okay, it's secret, like you can see in the configuration as well. And with that information, I easily can enter it here and perform the OSPF handshake again. So you will see, okay, the state is changing. The OSPF handshake is on its way, and after a few seconds, I will be in state full, get all the routing information. I will show up as a new router in this routing domain, and also I can easily inject whatever routing information I want to inject.
Yeah.
Okay.
Good. That was one of the features he implemented, not in Python for performance reasons. And so you see there are mitigating controls provided by the routing protocol itself. Use authentication to be sure there are no fake routes, whatever. But as you see it in a typical environment, if there is an authentication, it has a weak password, and then it's just a matter of time to brute force it and again be able to play around with the routing information and perform some attacks on that.
Yeah, these attacks can also be performed offline, so you just need to sniff one authenticated packet or one authenticated OSPF packet, and with that one single packet you can perform this attack at home. You don't need to stay connected to the network. You just need that single packet, and afterwards brute forcing against the password, and after some time you will find the right password.
Good. Then let's continue. So we showed you some attacks about for commonly used interior gateway routing protocols, namely OSPF and enhanced IGRP. Even the tool is also able to circumvent several implemented authentication methods, whatever. So the point of us is not just breaking stuff. So as I told you, the idea behind Loki was to close the gap between theoretical stuff and practical stuff, but not only for the reason so you can break networks, but also for the reason to make them more secure, to make your customers or other people believe that it's a problem, so they fix the stuff and somehow. So let's also have a look at what actually can be done against that kind of attacks. So there's not only a problem, there also should be a solution. And if you select a solution for a problem, you should also always mention about the operational impact it gets. So if it just improves your security a little bit, but operational impact, so you have to do a lot of stuff, it gets really complicated, whatever, then it's maybe not so a good idea to implement such a feature. So let's have a look at this stuff. There can be used authentication. We just saw it's crackable, but the amount of time it takes highly depends on the quality of the authentication key, of the quality of the password. So if you use authentication, if you have a protocol supporting authentication and use authentication and have some good password, and also don't forget about the usual things, how to handle passwords, don't write it on somewhere or sell your routers with still the password configured, whatever, and clear them before that, then it can be a pretty secure thing. Yeah, you just have to think about how to implement that. And it's not that hard to implement an authentication on OSPF. It's mainly one configuration line each router to set that kind of password. Within the category of access controls, you can also, with some routing protocols, you can also configure something called static peers. So that's based on an IP address. So I manually set my neighbor routers, and I will not accept any routes from other IP addresses. It's just a manual kind of access list. Okay, these routers can send routing information, other IP addresses don't. So he would not be able to, or the router would not accept routing information from his laptop. In such a scenario, we had to, let's say, DOS one router away so we can use its IP address, then maybe it would still work. For some routing protocols, there's a mechanism called passive interfaces. If you configure an OSPF routing process on a Cisco router, you add your interfaces to the routing process, and the routing process automatically takes the IP addresses from that interface. Okay, I know that network, I will propagate it to my neighbors. And if it's a client network, there's mainly no need to speak OSPF actively on that interface, but there's still a need to activate it because else the network won't be propagated to the neighbors. And that's also one configuration command on a Cisco router to say, okay, this is a passive interface. Propagate the network to the other routers, but don't speak OSPF or the routing protocol on that network. So if someone tries to send routing information over this interface, I just discard it, I don't accept it. So that's also a good measurement to prevent injecting false rules. Of course, you can use isolation mechanisms like using different routing protocols. So if one gets a route injected, it doesn't affect the whole network. But that's one of the features that's not so good for your operation if you don't have to if you have to manage one routing protocol, it's one thing, but if you say, okay, I use enhanced IGRP in this part, I use something else in this part, then it gets really complicated. You have to have, your administrators have to have knowledge from each routing protocol, so that's maybe not a good point. So I'll speed up a little bit. What's also not bad is IP-based peer filtering. I can put some other access list not based on the routing protocol, but based on some firewall rules, access lists and interfaces, stuff like that, to prevent routes coming in from wrong hosts. Or I can just say, okay, I'm route filtering, I'm accepting updates for this or that network, but not for, like he just did it, introducing a new network or something like that. Other things you can do, of course, you could encrypt the stuff using IPsec between routers, but as you can imagine, it would increase the operational stuff needed to operate such a network. And it's more likely you have some availability problems because of some IPsec not working properly, stuff going wrong, and would have been more impact on your availability in your network at all. And another point is visibility, just log stuff like that. So you see if somebody is injecting routing information. But yeah, as everybody knows, logging in big environments, okay, there maybe is logging, but does anybody look at logs or analyze them? Probably not. So there's some other stuff, more advanced stuff we also implemented in Loki. Or yeah, let's say some additional protocols, not only routing protocols, like it's VRRP, it's BFD or LDP. I will tell you something about the first two. Yeah. So VRRP, maybe some of you know this, it's just some kind of first hop redundancy protocol. So you can have, let's say you have a client network, there's a router with, let's say, we have an IP. So if this router fails, the network can't communicate to the outside world anymore. And it's a really simple protocol. You just put two routers there, having their own IP addresses, sharing one virtual IP address, and if the one router fails, the other takes over. Yeah, the systems can still communicate. What we will do here also is traffic redirection. So we also participate in the VRRP process between the routers and get the master, so get all the traffic from maybe the clients and forward it to the real router to intercept this traffic again. So it's another possibility to redirect traffic in the network. It's really similar to Cisco's HSRP protocol, but this one is standardized and it's not proprietary. It was mainly, you see it most on some Firewall 1 based firewalls on Nokia platforms. They use VRRP for redundancy. It pretty much looks like that. You have some kind of two routers. They have all their own IP address, let's say the .10 and the .20, and they share a virtual IP address. And all the clients use that virtual IP address as, let's say, their default gateway. So if, let's say, this router has this IP address as a secondary, it's a virtual IP address, and it fails, the other one will take over, and the clients can still communicate. For that to work, they're just exchanging some hellos, some, I'm still there, and if the other router don't see packets like that, after some time, he will just overtake the virtual IP address. So, yeah, there's also a demo on this, so I will just stick on the demo. They use some kind of priority to figure out who's the master, who is the active router. And the highest, the baddest priority is the 255. And unfortunately, you can't configure this explicitly. The highest number on Cisco device is 254. 255 only gets in a special setup of VRRP used automatically. So, and what's in the next demo, we'll see traffic redirection using VRRP in a setup like that. So we have these two routers with these IP addresses. That's our virtual IP. We have this network attached. And what we'll see now is how we became the master of this VRRP construction. and redirect the traffic there.
Okay. So this is still the same router, and I got some VRP IP configured on this device. The virtual IP is the 100.2, and as you see, the device I'm actually connected to is in a state backup, and the master router is the second router in front, which is the 100.20. So it got high priority configured, but we don't care about this priority. So I will launch the tool up again and connect to the right network, and you will see there is the hot standby blinking, and there are some VRRP connections visible to the tool. So this actually is the connection. It's handled by the 100.20, and the virtual IP is the 100.2. It got the priority 254. So what I will do next is doing a lot of pings from the one router to the virtual IP. While these pings are running, I will take over that IP address, and you will see there is only one ping missing, and all the other packages got directly forwarded to my notebook. So I will do a ping on the virtual IP address, which is the 100.2. I will repeat them sometimes. So, and while those pings are running, I will just take over the IP address. So now you see there is one ping missing, and afterwards all those other ICMP packages are now answered by my local host, not by the second router, which should be the master device. We can easily prove this if we take another look on the output of the show VRRP, and you see the master router now isn't the second router in front, but is my notebook, which got the IP address 100.100, and also the priority raised up to the maximum value, which is the 255. So as you see, it's kind of really easy to overtake an high available IP address if you see those VRRP traffic in your client network.
Okay. So for VRRP, there are also, like for some routing protocols, there were some authentication mechanisms, but they were removed in a newer version of the standard because they analyzed all the scenarios, and they mentioned, okay, if you use that, you more likely have denial of service by authentication not working properly or something like that. So both of the routers think they're the master, have the same IP address, and then that's it with your connectivity in that network. So they just removed it, and there's no really authentication in this protocol anymore. Good. Last but not least, the BFD. I have to speed up a little bit, so I will just scratch on that. We also don't make a demo on that, but unfortunately it's implemented. BFD, it's called bidirectional forwarding detection. It's, let's say, an add-on to the routing protocol because of the need of a faster, now I'm missing an English word. Faster, let's say, repair time for network protocols. So if a link goes down and it was your active route to a certain destination, it takes some time until the routers are noticing that the link is down. If it's a direct link, they pretty much notice it because you pulled the cable, so there's no link anymore. But if it's behind another router, they don't get that information. It can take some based on depends on the configuration, can take some seconds, can take some minutes. But there are, in some environments, there are requirements to do this a lot faster. And actually the routing protocols don't support that. So there was some kind of add-on. You can use it with different routing protocols. They can send, similar than the hello packages routers send to each other, they can send like something like hello packages every 50 milliseconds. So they can repair the network if something happens. They can really detect it really fast, let's say in 100 milliseconds, and switch over to an alternative route. Yeah. So you can realize repair times in your network within 100 milliseconds, or let's say 200 milliseconds, depends on how fast the routers are speaking that protocol. This is normally also implemented in hardware because software is still not that fast. We can also speak that, because if a router speaks that or wants to speak it with the neighbor, we have to speak it with our tool also, else the router won't speak with us. So we have a real fast failover detection with this kind of protocol. It works something like that. And they send every 50 milliseconds, they send packages to their neighbors, both of them do that. And if there are no packages coming in for a configurable, let's say 3 packages missing, you can configure that, then the route is, or the link is configured dev, and the router can switch to an alternative route. And that's also, it's the time it got an RFC standard, it's just 2 months ago. Then you just read some blog and saw, hey, there's a new protocol, new add-on to routing protocols, and just looked at the packet format. Oh, it's easy, and 3 or 4 hours later, it was implemented. So you will probably not find it in the wild already because it's a pretty new standard, but it will for sure it will show up in some environments having high requirements on failover times, which cannot tolerate a downtime from a minute or something like that. Then most likely this protocol will show up there, and Loki can handle this attacks too. So, So what's going on with Loki? Loki is still work in progress. So there are lots of protocols already implemented. There will be upcoming features, which mainly are new protocols. Already on the to-do list are stuff like ISIS, GLBP, SNMP to implement. And just to complete the suite, we will also add protocols already supported by other programs like VTP or DTP attacks, spanning tree attacks, DHCP. There are several tools already supporting that, but to complete the suite, to have one suite to attack infrastructure protocols, we may add them also. And whatever infrastructure protocols we need to support to attack, they will maybe get implemented. If you have some suggestions, maybe, there's an infrastructure protocol nobody can attack, there's no tool, but it should be possible, just drop us an email and we will implement that stuff also. And of course there will be bug fixes. The whole tool is released today, now, for the first time in the world, except mentioned 2 modules which have some legal issues, so we can't release them yet. Maybe we'll do, maybe we will not. Current version is 0.24, and that's the link where you can download the source code. And we also built some Ubuntu and some Gentoo packages to be easily installable. So if you want to play around with that, just install some Ubuntu Live distribution, grab the packages, install them, and then you can play around with that. Maybe there will also be Windows version or a Mac version. We're not sure about that yet, but maybe we'll do that too. Conclusions. So let's call Loki a new kid in the infrastructure attack block. So a new tool closing another gap between theoretical attacks, make it impractical, usable. I know the attacks on OSPF and Hansa GRP, it was no secret that it's potentially attackable, but now you can use it with some mouse clicks with an easy tool. And another thing we want to tell you, okay, now it's possible to attack these protocols, so protect your infrastructure, but always think about the operational impact. Think about what does it mean for the guys operating your network if you implement the new security features, and don't just implement everything some smart white papers tell you or recommend you to do. So always get a good mixture of improving your security, but don't highen up your operational things you have to do. And also about, because of the infrastructure modularized infrastructure, go out and write your own local modules. You can write them in Python. It's not that difficult. For sure you have to know the protocol, but you can implement other modules, maybe in a cracker for other hashes, or whatever you need. And of course, have fun at the Blackhat. And thanks for your time, thanks for coming around. Hope you enjoyed the talk. And yeah. A last point, thanks Ollie for contributing the real CCP work. It was part of his diploma thesis to figure out that stuff, and Flo for all the awesome iCandy editor technical presentation. He pimped it a little bit with all the nice pictures and stuff. He has can quite do this really good. So also thanks to these guys to contributing that stuff. Thank you.